Welcome to Introduction to Geology. I'm Dr. William Patterson. In this module, we'll be discussing plate tectonics and plate boundaries. Let's talk boundaries. Divergent boundaries are where plates move apart. Within ocean basins, divergent boundaries tend to be narrow rifts that approximate the idealized version of how plates spread apart. In ocean spreading centers, on the seafloor, the boundary between separating plates is marked by a mid-ocean ridge. This is an undersea mountain chain that exhibits earthquakes, rifting, and volcanism, all caused by tensional, stretching forces of mantle convection that are pulling the two plates apart. As the seafloor spreads, hot molten rock, known as magma, wells up into the rifts to form new ocean crust. At this spreading center in the mid-Atlantic ridge, the North American plate and the Eurasian plates are separating. On the island of Iceland, we see a segment of the otherwise submerged mid-Atlantic ridge. This allows you to actually walk between the two plates as they separate. If you have the same wingspan as me, you can touch the Eurasian plate and the North American plate at the same time. The Mid-Atlantic ridge continues in the Arctic Ocean north of Iceland, and to the south it connects to a nearly global system of mid-ocean ridges that wind through the Indian and Pacific Oceans, finally ending at the west coast of North America, where the spreading center was subducted. Seafloor spreading at these mid-ocean ridges has created the millions of square kilometers of ocean crust that now form the floor of the world's oceans. The oldest ocean crust that's still in an ocean is less than 200 million years of age, so that's all fairly young rock geologically speaking. In continental rifting, the early stages of plate separation are readily visible in the Great Rift Valley of East Africa. These divergent boundaries are characterized by rift valleys, volcanism, and earthquakes, and they're spread out over a wider zone than what we find in ocean spreading centers. The Red Sea and the Gulf of California are other examples of rifts that are further along in the spreading process. In these instances, the continents have separated enough for new oceanic crust to form along the spreading axis, creating a deep basin into which the ocean has poured into. Sometimes continental rifting shows or stops before the continents actually split apart. In Europe, the Rhine Valley is an example. The border between Germany and France is a weakly active continental rift that is a kind of failed spreading center. Whether the East African rift continues to open, causing the Somali subplate to split away from Africa completely and form a new ocean basin, has happened between Africa and the island of Madagascar, only time will tell. Will the spreading center slow and eventually stop, as appears to be happening in Western Europe? We don't know the answer. Other failed rifts are present in North America, across the US and Canada. In convergent boundaries, lithospheric plates cover the globe, so if they separate in one place, they must converge somewhere else if the Earth's surface remains the same size. Where plates come together, they form convergent boundaries. The geologic processes that act during plate convergence make these boundaries more complex than other boundary types. In the example of ocean-ocean convergence, if the lithosphere of both converging plates is oceanic, one plate descends beneath the other in a process known as subduction. The lithosphere of the subducting plate sinks into the asthenosphere and is eventually recycled by mantle convection. This sinking will produce a long, narrow, deep-sea trench. In the Marianas Trench of the Western Pacific, the ocean reaches its greatest depth of about 11 kilometers, deeper than the height of Mount Everest, which is around 8.8 kilometers. As the cold slab of lithosphere descends deeper into the Earth's interior, the pressure on that slab will increase. Water trapped in the rocks and the sediment is going to be squeezed out, and it's going to rise into the asthenosphere above the slab. This fluid causes the mantle material above it to melt because it's getting wetter and it's decompressing. The resulting magma produces a chain of volcanoes known as an island arc behind the trench. The subduction of the Pacific plate has formed the volcanically active Aleutian Islands west of Alaska, as well as the Mariana Islands and other island arcs in the Western Pacific. The lithospheric slabs driving into the mantle cause earthquakes as deep as 690 kilometers beneath some of these island arcs. These are exceptionally deep earthquakes. In the example of ocean-continent convergence, if one plate has a continental edge, it overrides the oceanic lithosphere of the other plate because continental lithosphere is less dense, thicker, and therefore less easily subducted. The submerged margin of the continent is crumpled by the convergence, deforming the continental crust and uplifting rocks into a mountain belt roughly parallel to the deep-sea trench. The enormous compressive squeezing forces of the convergence and subduction generate great earthquakes along the subduction zone. Over time, materials are scraped off the descending slab and incorporated into the adjacent mountain belt, leaving geologists with a complex baffling record of the subduction process. Like we saw in the case of ocean-ocean convergence, the water carried downward by the subducting oceanic lithosphere causes mantle material to melt. The resulting magma rises as a diapir and forms volcanoes in the mountain belt behind the trench. A great example, the west coast of South America, is where the South American plate converges with the Nazca plate in a subduction zone of this type. The Andes Mountains, second highest in the world, rise above the continental side of this convergent boundary, with a deep sea trench lying just off the coast. The volcanoes here are active and quite deadly. In one example, Nevado del Ruiz in Colombia, 25,000 people were killed when it erupted in 1985. Some of the world's largest earthquakes have also been recorded along this boundary. Another great example is the Cascadian subduction zone, where the small Juan de Fuca plate converges with the North American plate off the northwest coast of North America. This convergent boundary gives rise to the dangerous volcanoes of the Cascade Range, such as Mount St. Helens, which last erupted in 1980, and again in a minor eruption in 2004. There is increasing concern that a great earthquake will occur in the Cascadia subduction zone, causing devastating damage along the coast of Oregon, Washington, and British Columbia, a highly populated region. Such an earthquake could cause a disastrous tsunami as large as the one generated by the Great Tohoku earthquake of March 11, 2011, which occurred in a subduction zone off northeastern Japan. In continent-continent convergence, where two continents converge, the kind of subduction seen at other convergent boundaries cannot occur. The geological consequences of such a continent-continent collision are impressive. The collision of the Indian and Eurasian plates, both continents at their leading edges, provides the best example. The Eurasian plate overrides the Indian plate, but India and Asia remain afloat on the mantle. The collision creates a double thickness of the crust, forming the highest mountain range in the world, the Himalaya, as well as the vast, high Himalayan plateau, about the size of the continental U.S., but punched up to nearly 20,000-foot elevation, or higher at the edge. Severe earthquakes occur in the crumpling crust of this and other continent-continent collision zones. It's very common to observe large earthquakes along the Himalayan front. Many episodes of mountain building throughout Earth's history were caused by continent-continent collisions. The Appalachian Mountains, which run along the east coast of North America, were uplifted when North America, Asia, Eurasia, and Africa collided to form the supercontinent Pangaea about 300 million years ago, the time of the Mesosaurus. At boundaries where plates slide past each other, lithosphere is neither created nor destroyed. These boundaries are transform faults, fractures along which plates slip horizontally past one another. Our best example is the San Andreas Fault in California, where the Pacific plate slides past the North American plate. Another example is the Alpine Fault, which slices through the South Island of New Zealand. Because the plates have been sliding past each other for millions of years, the rocks facing each other on the two sides of the fault are of different types and ages. Large earthquakes, such as the one that destroyed San Francisco in 1906, can occur along such transform faults. These are often vertical and delineated by their seismic activity. There's considerable concern that within the next several decades, a sudden rupture of the San Andreas Fault, or a related fault near Los Angeles and San Francisco, will result in an extremely destructive, deadly earthquake. Transform fault boundaries are typically found along mid-ocean ridges where the continuity of a spreading zone is broken and the boundary is offset in a step-like pattern. An example is found along the boundary between the African and South American plates in the central Atlantic Ocean. Transform faults can also connect divergent plate boundaries with convergent plate boundaries and convergent plate boundaries with other convergent plate boundaries. We can form combinations of plate boundaries, each plate bordered by some combination of divergent, convergent, and transform fault boundaries. To make things more complicated and confusing, we can combine plate boundaries. Each plate is bordered by some combination of divergent, convergent, and transform fault boundaries. An example, the Nazca plate is bounded on three sides by spreading centers, offset in a step-like pattern by transform faults, and on one side by the Peru-Chile subduction zone. The North American plate is bounded on the east by the Mid-Atlantic Ridge, a spreading center, and on the west by subduction zones and transform fault boundaries.
Meanwhile, back in the year one, when you belonged to no one, you didn't stand a chance, son, if your pants were undone, 'cause you were bred for humanity and sold to society. One day you'll wake up in the present day, a million generations